Okay, hello. Good afternoon, evening, morning, good whenever you're watching this. This is part one of lecture two for Life in the Universe. That means this is material we would cover on the second day of class if we were meeting in person. Now, I believe I told you in the previous set of videos that in person, when you came into the classroom, I would have up on the screen an alien of the day, typically from science fiction, but not quite always, that spend a few minutes just for fun talking about, along with appropriate music to go with it. And for our first alien of the day, I have one of the most famous fictional aliens, Mr. Spock from Star Trek, as shown in the original series portrayed by Leonard Nimoy on the left, and in the reboot movies of a few years ago by Zachary Quinto, which was pretty good casting. In general, I'm not thrilled with that particular set of movies. Anyway, the portrayal of aliens in science fiction is often much more about ourselves than about how aliens, if they exist, are likely to really be like. And interesting with Mr. Spock, in the 60s, when the character was first introduced, he was quite controversial with the NBC network executives, even though basically just a human actor with a little bit of makeup and a silly haircut. Apparently, the executives were quite concerned that audiences would find him too frightening and would be unable to see him sympathetically. And of course, he turned out to be one of the most popular characters. And I guess worried that American audiences would be afraid of Mr. Spock in the 60s kind of shows how our culture has changed a bit. I'll have one soon, maybe next time, that will be much more frightening than Mr. Spock. Let me remind you, I'm going to only have these aliens per lecture, not per video. So after the series of videos that make up this lecture, you'll get the next alien. And anyway, music I'd be playing to go along with this would be the theme song from the original Star Trek series. And I'll have a link in the description if you want to go listen to it on your own. All right, so what we're going to do for the next two classes, so this lecture and the third lecture, so be at least 4 videos overall, maybe a little bit more, is we're going to try and get an overview of the universe and of life, the two big aspects of our topic for this course. In this lecture, so this video and the following one will be about the universe, and the next series of videos making up the third lecture will be an overview of life. Now, some of what I'm going to tell you in these lectures for this unit will be which is Unit A, will be stuff that we will come back to later in the course at different angles or in more detail. And there are some other things, particularly in this part of it, that are not directly relevant to our overall subject. So this will be the only time in this course we will take a look at it. Well, for our motivating pretty picture for the universe, I have an image here called the Hubble Ultra Deep Field. So what they did is they took the Hubble Space Telescope, pointed it at a spot on the sky that didn't have anything obviously bright in it, and took a series of long exposures which they combined into a single image. There's actually more than 11 hours of total exposure time with the Hubble Space Telescope went into making this image. This covers a very tiny patch on the sky, only a couple of arc minutes across. That's about the smallest little patch you could distinguish with your eye. And it turns out there are about 10,000 visible objects in this figure, in this image. A few of them, if you can see my cursor, that have these kind of sharp, look like circles with these sharp points on it, those are called diffraction spikes. That's an optical effect from the telescope when used to view something that appears to be a point source. Those are foreground stars in our own Milky Way galaxy. There are a couple of obvious ones there. There's another one at the bottom of the picture there. And if you look carefully, you can probably find a few more. But nearly all of the 10,000 objects in this view are galaxies at much greater distances. You see a few of the closer ones, which are brighter. You can see some structure too. This one right here is a nice spiral. Some of the others are just really faint little smudges that you see here. Those would typically be the much more distant ones. Each one of these galaxies typically contains tens, if not hundreds of billions of stars. Anyway, we'll take a little bit at the end of this lecture, the end of the next video, at how many galaxies there may be in the observable universe. Okay, now, one thing we've known about the universe for about 100 years is that it is expanding. The universe itself is getting bigger. As it expands, the average density and temperature of the universe are decreasing. So the universe is cooling and becoming more rarefied as it expands. I'm sure you've heard the term Big Bang before, even if just for the title of a popular sitcom. It refers not to an explosion of any type, but just to the very hot, very dense state of the entire early universe. Most of what we know about the early universe comes from calculating what would happen if you ran the expansion backwards in time. What we get as the age of the universe is how long ago it would have been where everything would have been at the same point. And we have that measured pretty well now at being about 13.7, 13.8 billion years old. Incidentally, the Big Bang, if you ask where did it happened everywhere in the universe because it was the entire universe this early time. Now, early on, the distribution of stuff would have been very nearly uniform, but not quite perfectly. And it appears that tiny variations in the density of the material in the early universe served as seeds for the formation of the structures that we see today. So the regions that were slightly denser would have slightly stronger gravity and draw more material towards them, so they would get denser on average as time goes on. And that's what gives us stars, galaxies, clusters of galaxies, etc. today. In the last 20 years, we've finally identified what the universe seems to be made of, at least kind of counting all the parts of it. Mostly it's this stuff which we've only known about for about 20 years that we call dark energy. And really all we know about it is that it makes up about 70% of the stuff of the universe, and it's causing the expansion of the universe to accelerate and has been doing so for a few billion years. But other than that, we don't know very much at all about it. In case any of you want a Nobel Prize in physics, figure out what the dark energy is and convince everybody else you're right, and I guarantee you that will be a Nobel Prize in physics. We've known about it longer than the dark energy, but another mysterious component we call dark matter, which is about a quarter of the stuff in the universe. We don't observe it directly, but we can see its gravitational effects on other matter, and we also know very little about it. So another way to get a Nobel Prize in physics is figure out what the dark matter is and convince everybody else you're right. About 5% of the universe is what we might call baryonic matter. Baryon is a fancy term referring to a class of subatomic particles, including protons and neutrons. You probably know we're made up of protons, neutrons, and electrons. Electrons aren't baryons, but most of our mass is in the form of our baryons. So we are made out of baryonic matter for the most part, at least as far as mass is concerned. We understand that pretty well, but it's only makes up about 5% of the stuff in the universe. Now, speaking about protons, neutrons, and electrons, one does have to deal in astronomy with the very small as well as the very big. And if you happen to be watching this on a phone screen, this picture, at least reading the captions on, is probably very difficult. I would recommend you watch these videos on a computer screen if you can. If you can't, for any figures that you can't read, if you look at the lecture notes on the course website, the images will be there, and then you can magnify those on your screen. But this is a kind of a cartoon view of an atom. You probably learned about atomic structure sometime in high school or middle school, where most of the mass of the atom is in the protons and neutrons, which make up the very, very small nucleus, and then the much less massive electrons surround the nucleus. I've represented the atom here as a fuzzy donut to represent where the electrons in this atom most likely are, and indicating they're most likely in that region of the fuzzy donut. We'll talk more about that when we talk about matter and our energy, matter, and light unit, which I think is unit E. All right, if we're in the classroom, I'd point at this on the wall and say that every science classroom should have a periodic table on it. Well, here's one on the screen. You probably know periodic table is an arrangement of the elements according to their chemical properties, where anything in a given column is chemically similar to everything else in that column. And what that means is for atoms, say, of these elements, including carbon, silicon, germanium, tin, lead, and this isn't up to date. I don't know what name we've given 114 off the top of my head. But they all have the similar arrangement of their outer electrons, which is what interacts with other atoms. What determines the element, the way we define it, what element it is based on the number of protons in the nucleus. This number you see over each element, that's how many protons it has in the nucleus. You can have variants of atoms of the same element, same number of protons, will have different numbers of neutrons. We call those variants isotopes. This will be important when we talk about stars. So we have to learn a little bit about how stars work, as we'll see shortly. All right, you probably have not seen a plot like this one before. So we have the atomic number, the number of protons of a nucleus on the horizontal axis, and the vertical axis is a measurement of the relative abundance by number of atoms in the solar system, which is about the same as it is in the universe as a whole. On a logarithmic scale, so each step here is a factor of 10 more abundant than going a step further down. So there's about 10 times as much hydrogen as there is helium. And you'll notice that hydrogen is by far the most common element in the universe, followed by helium. Lithium, beryllium, and boron are pretty rare. Carbon, nitrogen, and oxygen are fairly common, but not as much as helium and hydrogen. And then notice you get this kind of up and down variation with a gradual decrease in abundance until we get to this peak around iron and nickel. And then after the iron and nickel peak, it drops off fairly rapidly. So these heavier elements here are generally not very common. We actually have a pretty good understanding of why this distribution is the way it is. And it mostly has to do with our understanding of stars. Now, one other thing about the very early universe, it turns out that when the universe was less than about 1/100th of a second old, it would have been too hot for any atomic nucleus to be stable. So you'd only have free protons and free neutrons. But once nuclei become stable, where the universe cools to the point where that's possible, it's still hot and dense enough for another few minutes for nuclear reactions to take place to build up some heavier elements from what start off as protons and neutrons. So what you make is a fair bit of helium. In fact, most of the helium in the universe comes from this first few minutes, and trace amounts of some other isotopes of hydrogen and helium, and one particular isotope of lithium. But most of the material ends up still in the form of hydrogen after this. And it turns out that nearly all of the other elements have been produced by stars. So if I back up to the 2 slides here, oh, that's 3 slides, just 2. Then except for, like I said, hydrogen, most of the helium, and some lithium, beryllium, and boron, everything else here, including some helium, some lithium, is made in stars. So one of my favorite things about astronomy is that we are literally made of star stuff. I do not mean that in any metaphorical or poetic sense. I mean it in what the word literally actually means. So that means the calcium in your bones, and teeth, the iron in your blood, the carbon, nitrogen, oxygen, phosphorus that are so important for biomolecules, every atom of that in your body was at one time in a star. So that means, I guess, we're going to have to concern ourselves in this course a bit with what stars are. So a star, if I had to define it in one sentence, you see it right there. It's a gaseous object that has sufficiently high internal temperatures to maintain nuclear reactions in its interior. There are these star-like objects called brown dwarfs, which we can think of being intermediate between stars and planets that are not able to maintain nuclear reactions, but they're not quite the same as planets. We'll learn a little bit about them. And we'll also see that matter actually gets cycled throughout successive generations of stars. So as this happens, it gradually adds to the amount of elements heavier than helium in the universe. It also turns out that the probability that a planet could have life depends a lot on the nature of the star that it orbits. So for that reason, later in the course, we are going to spend some time learning a fair bit about stars. Now, at this point, this is a good point to break the video and finish this lecture in another video, which means I need to give you the attendance secret code for this video. And it's Nervous Charlie's, which is an establishment I visited a few times in Tennessee. It is both a gas station and a fireworks store. So it is very appropriately named. So email Nervous Charlie's to me to get the credit for watching this video. Let me remind you, if you should have any questions, be sure and email me, and I'll do my best to answer them. I'll stop the video share here for just a second. So I will see you in the next video, which I'm going to record after I check the email that I have just gotten. So I'll see you in the next video.